So that's those two things. Then we've enabled the interrupts. So at this point here, we've enabled the interrupts. The 8, if you switch to binary, that's the most significant bit been switched on. That's the global enable. And if you convert this to binary, this should be the bit associated with timer 0, enabling timer 0 interrupts. And then we start the timer running. And then we go into our main program, main loop, and we just sit here doing nothing important, basically jumping around here forever. Now, we could actually be doing some other useful work down here, but in this example, we're not bothering with any other useful work. At some point, that timer's running in the background. At some point, it will overflow. You'll notice that there's no code here to basically check the TF flag, because we don't need to do it now. Basically, the interrupt hardware is going to do that for us. So we don't need to do any polling associated with the timer. We can get on and do other things. However, when that timer overflows and that flag gets set, that flag will automatically trigger an interrupt. We will then suspend the main program, and it will go to this memory location, flip this bit, and then return from the interrupt, clearing the interrupt flag. So there's a couple of things there. One is we're not testing the flag. That's done automatically. The other thing, you didn't see me manually saying clear TF0. When we've been doing polling before with the timers, we've had to clear the flags. If you use the timers using interrupts, the interrupt routine itself will automatically clear the flag for you. So you don't need to do it. If you do, it's not a problem, okay? So you can clear the flag if you want to, but it's not needed anymore. So we would then basically come out of this interrupt routine, and then we would come back to everywhere in the main program and sit there again. And yeah? TR is to start the timer running. It stands for timer run, and it's a bit in the TCOM register. So what we've done here is we've configured the TMOD register for 8-bit auto reload. The reload value we've put in the upper half of the timer here. We've enabled the interrupts here, and at this point we've started the timer running. And we don't bother stopping it, we just let it run forever. And it will basically, every 92 machine cycles, it will leap into here, toggle a bit, and come back down here again, and it will do that forever. Okay. So we've talked about the timers. You now know 2 ways of playing around with timers. Well, you know lots and lots of things about timers. You've used timers as counters, timers as timers. You know about all the different modes of timers. And we've got 2 ways of monitoring when the overflow takes place. We can poll the TF flag, or we can use interrupts so that when the TF flag gets set, automatically we're taken to an interrupt service routine. Okay. The advantage of the interrupt routine, by the way, is you could be doing other useful work while the timer is counting up. You're not having to keep checking the flag. So it's almost as if you're doing 2 things at once. The timer's doing its thing, doing its counting, and the CPU can be doing something else useful. It might be doing an addition, or it might be fetching some instruction from somewhere else and doing useful work. But you can rest assured that you won't miss the timer overflow, because that overflow flag is linked to hardware that when it does overflow will stop the main program doing what it's doing. We often use interrupts in real-time systems where if something happens, we don't want to have to wait a long time to respond to it. And the nice thing about interrupts is, as soon as one of those interrupts happens, you take control of the program, pause it, and go somewhere else and deal with the interrupt straight away. So you can end up with a very responsive system. Okay. So, putting timer interrupts to one side. Now, there are 2 other types of interrupts, well, 3, but there's 2 associated with external pins. These are part of port 3, and there are alternate functions for 2 of the pins on port 3. So this is port 3. So, and they're known as int 0 and int 1. You may see them sometimes written as x0, x1, doesn't really matter. Interrupt 0, interrupt 1. Basically, you can connect some external hardware over here so that when your external hardware has completed something useful, it can basically set this pin in a certain way to basically get the attention of the 8051 so it can basically read something from that piece of hardware, do something like that. So they're very useful for when the 8051 is controlling other devices to get the 8051's attention to handle, to process, to do something with these external pieces of kit. So you only got 2 of them. If you had lots of pieces of external hardware, you could, for example, do this kind of thing, where they all come into an AND gate, and that all feeds into, say, one interrupt. Normally, we would assume that all of these are kind of high or whatever, but if any one of them was to go low, it would pull this low and trigger the interrupt. Of course, when that happens, you've got to use some additional method to test them all to find out which one actually caused the interrupt. But that's possible to do that quite often. So although we've only got 2 interrupt pins, it doesn't mean that we can only control 2 devices through interrupts. There are ingenious ways around that with a little bit of extra hardware to allow you to control lots of things in an interrupt-driven way. Anyway, in terms of these 2 external interrupt pins, they actually have 2 modes of operation. 2 ways that you can trigger the interrupt. You can trigger them when you reach a certain level, and there's only 2 levels, high and low, and in level triggered, it's triggered when the level goes low. You can't control it, say, I want it to be triggered when it goes high. Intel have decreed it's when it goes low that it triggers. If you want it the other way around, you have to put an inverter in. The other one is edge. And in edge triggered mode, it's a high to low transition that triggers the interrupt. So each of these 2 pins can be configured for level triggered interrupts or edge triggered interrupts. And how do you decide which to use? We looked at a register a while ago called TCON, and so far we've only really looked at the upper part of it. The upper part of it has the run flags and it has the overflow flags. The lower 4 bits actually are used to configure these 2 external interrupts. And there's 2 bits in here, I don't know which ones they are, which stand for, I'm trying to think what there's an acronym for it, but anyway, we'll say it's the type of interrupt. So it'll be the type of interrupt for 0, the type of interrupt for 1, these external interrupts.
On the level trigger,
yeah.
If it's continuously low, does it continuously trigger?
I'm going to come on to that anyway, but basically, when it goes low, it will trigger the interrupt. It is up to you to make sure that by the time your interrupt routine finishes, it's no longer low. If it's still low, as soon as you come out of the interrupt routine, you go back into it again. So it's you as the programmer has to make sure that that's the case. Now, if you don't know how long it's going to take, and you're worried about that, it would make sense to use edge triggering. Because in edge triggering, the interrupt would cause it to go low, but in order to get the next trigger, it can't, being low isn't enough. It has to go high again and have another high to low transition. So that's a situation where we might prefer to use edge triggering. But if you are using level triggering, and if the level remains low, and your interrupt routine finishes, as far as it'll automatically straight away re-trigger the interrupt routine, you go back into it. There's another limitation on level triggering. When it does go low, it has to go low for typically about 4 machine cycles. So if it goes very quickly and back high again, in less than 4 machine cycles, it might not trigger the interrupt. Okay. So that's this point here. So in level triggered, the signal has to be high again by the time the interrupt routine finishes. Otherwise, we'll regenerate the interrupt. And when it does go low, it has to be low for at least 4 machine cycles. In the case of level triggered interrupts, those 2 bits are the only things that matter for switching these external pins into level triggered mode. If they happen to be in edge triggered mode, so the type chooses whether you're doing level or edge, there are another 2 bits in here that matter, but they only matter if you're doing edge triggering. Basically, there are a couple of flags, and when an edge triggering event happens, the flag will get set high. But it will only happen if you have chosen to use edge-triggered external interrupts. So if you've chosen for this interrupt 0, you said, I want this to be edge-triggered. When that goes from a high to low, another bit in this register, another bit in here will go high, which will be the IE flag, I think it's called, which is interrupt edge, associated with that interrupt. It will go high to tell you that the edge has happened. And that will trigger the interrupt.
If the pin is high,
Yeah.
and then you make it low,
Yeah.
doesn't that make it a edge trigger, but you want a level?
The difference between it, if you selected either edge or level, if it was high and went low, that would be sufficient to trigger it in either mode. That's true. The question is, if you kept this going low for a long time, what would then happen? In the case of level triggered, once you'd finished your interrupt service routine, if this was still low, you'd immediately go back into the interrupt again. In the case of edge triggered, you wouldn't, because it's only the transition from a high to low that causes the triggering.
So after 4 machine cycles, you have to put it high.
So after 4 machine cycles in the level triggered one, it needs to go high. When it goes high, it doesn't matter too much, provided it goes high before the end of your interrupt service routine. And if you're not sure about it, you're using some external hardware and you're not sure how long it's going to take for it to go high again, you're probably better off using edge-triggered interrupts. Okay, so here's an example of a program using level-triggered external interrupts. So what's this going to do? So every time we've got an LED, which is connected to port 1, and whenever interrupt 1 goes high, then we want that LED to come on. Is it? Whenever interrupt pin goes low, we want this to come high for a little bit, the LED. Okay. So let's just work our way through the code. So you'll be familiar with this kind of structure now. So at location 000, we put a jump to the main program over here. At location, and now in this case, notice that the origin here is not 000B, which we had before, because that's to do with timer interrupts. This time when this interrupt happens, it will jump to this memory location. So that's why we've had to put the start of our interrupt routine here. So at location 0013, this is the start of the interrupt service routine. First of all, it's going to set the pin associated with the LED. And then we could put in a little delay loop. We're loading up register R3 with a number, decrementing it, and just jumping around here until it reaches 0. When it reaches 0, we clear the pin, the LED, and then we return to the main program. So what will happen is when you press the interrupt, the pin associated with the interrupt, what you should see is the LED come on for a little bit, and then it'll go off again. That's all. Not very exciting. In the main program, we've started the main program address way beyond, we hope, where the interrupt service routine finishes. Okay? So it's starting at location 0030, which is a bit higher up in the memory. And here we've actually decided which interrupt we're going to switch on. 2 bits have been set, the global interrupt enable, and this pin, this bit, which is actually to switch on external interrupts associated with interrupt 1. And then the main program just sits here doing nothing. So every time you press the button, the interrupt happens, turns the LED on, counts for a little bit of time, turns the LED off, finishes the interrupt routine, and comes and waits here again, and that's it. Does that forever. I'll say some more things about when we go in from the main program into the interrupt service routine, the only things that happen in terms of the stack is the program counter gets put on it. And when you leave the interrupt routine, what's on the stack gets put back in the program counter. Now, inside your interrupt routine, in this case, I'm fiddling around with R3. If your main program is doing things with R3, we would have potentially a problem. So what you might often do, if you want to play safe with your interrupt routines, because you don't know where in the main program you are at the time the interrupt takes place. That's the whole point. It happens whenever this event takes place. So, a common practice when you invoke an interrupt routine is to start it with something like this. So, this is the start of our interrupt service routine. Let's say it's to do with int1, whatever. What you might do is do something like this. You are copying what is in R0 onto the stack, R1 onto the stack, R2 onto the stack, etc. You might wish to preserve the program status word, because that's not protected either. So you might, after pushing all those, you might push the program status word, because all of these things, if you're doing in the middle of an addition, or doing something else in your main program, and your interrupt service routine fiddles with any of the flags in here, or fiddles with any of these registers, your main program doesn't realize what's happened, and all of a sudden the numbers it was using have all changed. And it will cause the main program to misbehave. So, as we launch into the interrupt service routine, what we normally do is to copy all the important registers that we're going to be fiddling with. And at the end, then, you do whatever you do in your interrupt service routine. You can use all these registers again, it doesn't matter. At the end of the interrupt service routine, you have to put them back as they were. So you pop the program status word, you pop, now, it'll be all the registers to pop 1, pop 0, and then ret I, for example. Notice I'm having to do it in a very strict sequence here, because the stack is a last in, first out structure. So if I was to do push 0, 1, 2 and then pop 0, 1, 2, I'll have swapped all the registers over. That would be a disaster. So I have to pop them in reverse order to what I pushed them. So 0 goes on the stack, then 1 goes on the stack, then 2 goes on the stack. And when I pop them, I'm putting that back to R2, I'm putting that back to R1, and I'm putting that back to R0. The nice thing about doing this kind of thing, yes, it makes your interrupt service routine bigger, but you can rest assured that whatever you do in your interrupt service routine, it isn't going to mess up the main program. If you don't do that kind of thing, you've got to be very, very careful you're not fiddling with the same registers that the main program's fiddling with. And that might include things like the carry flag and so on. Okay. Don't want to nag you over that. So we've talked about external interrupts and making them level triggered. This is just a slide that's saying those external interrupts, instead of being level triggered, can be edge triggered. And if they are edge triggered, then these two flags that exist as part of TCOM have significance. So in TCOM, we have 4 bits, the lower 4 bits. 2 bits are used for enabling external interrupts. 2 bits are flags that only have meaning if you're using edge-triggered interrupts. If you have a particular interrupt set up for edge triggering and that edge appears, then the appropriate flag will be set high and trigger the interrupt. So that's all it's saying here. It's reminding you that these two extra flags don't do anything if you're doing level triggered interrupts. And also these flags which are set that invoke the interrupt routine on edge triggering will automatically be cleared when the interrupt routine finishes. Don't say anything else I want to say there. Right, so here's the same kind of code as before. Not quite the same, it's a buzzer this time. But this time we're using edge-triggered interrupts to control a buzzer that's attached to port 1.5, pin 1.5. So it's going to go on for a short period of time and then go quiet again. But rather than being based on the level, it's based on the edge, the falling edge of int 1. Similar kind of program structure before, so the main program we just put a jump beyond the interrupt service routine somewhere else in memory where the rest of the main program exists. This part of it is configuring it. Now, this bit about setting a bit in tcon bit 2 is actually the bit that's saying we want to make this interrupt edge triggered. So, although it's in the timer control register, it's got nothing to do with timers whatsoever. It's a bit confusing that way. And then in the interrupt enable register, we're switching on int 1 interrupts. But because we've set this bit here, the interrupt that is here will be an edge triggered interrupt, not a level triggered interrupt. And then the main program kind of just goes around here doing nothing. When the interrupt happens, which is a falling edge, then we'll leap into here, set this bit high, count down from R3 from 255 decimal. When it reaches 0, we come here, clear that bit, and then return to the main program. End of story. Okay. I did talk about this yesterday as well. So, as far as the 8051 is concerned, there are 5 proper sources of interrupt, and I suppose you could argue that reset is a kind of 6th almost kind of interrupt, but not a proper interrupt. The 5 proper sources of interrupt are external interrupt 0. I feel like this little piggy went to market. Timer 0 interrupts. External interrupt 1. Timer 1 interrupts. And then there's 1 interrupt flag to deal with the serial interface. And as I said yesterday, with the serial interface, there are 2 pins that belong to port 3, which are used for it, TXD and RXD. And they're both connected to a special buffer called SBUF, where S stands for serial buffer. There is actually a control register for that called SCON that we will go through in a week or two's time. If anything, that's going the wrong way around, isn't it? Silly me. If anything needs to be sent, all you could do is you just say move into SBUF, the contents, of the accumulator, for example. So if something was in the accumulator, you stick it in here, that will automatically be transmitted. You don't have to tell it to transmit. That's why we use this hardware support on the serial interface. It's quite nice. It will also clock out the bits at the appropriate rate that you've configured, but we haven't done about configuring the serial interface yet. At the end of transmitting that block of bits, it will set a flag called the TI flag, the transmit interrupt flag, to tell you it's finished sending that block of information. There is another flag so that if anyone was to send you any information, and by the way, this is full duplex, so you could be transmitting and receiving at the same time. If you happen to receive a byte of information that's deemed to be good, because you can use parity to check that if you want. If you have a good block of information that's received, the RI flag will be set. If you receive another block of information before you've read this out, you will lose it. So as soon as the RI flag is set, it's your job to copy the contents out of here and put it somewhere else. So you would do something like move into the accumulator the contents of SBUF, for example. both of these flags are connected to the same interrupt hardware. So if you've enabled the serial interface interrupt and it's triggered, you're not quite sure, has it triggered because I finished sending something, or has it triggered because someone sent me something? So what you would have to do is to check these two flags to find out which one has gone high. Whichever one's gone high, that tells you what triggered the interrupt. Okay? Now, we've seen other flags used with interrupts before. Generally speaking, flags which trigger the interrupts are automatically cleared by the interrupt service routine. But it isn't true in the serial interface case. So it's just a kind of quirk. Okay, so that's what this is, the TI flag and the RI flag. Right. It is quite possible that multiple interrupts happen at the same time or almost at the same time. If that is the case, you might be wondering, well, what happens? The Intel have decreed that if multiple interrupts happened at the same time, they will be processed in a strict sequence. And this is the sequence from highest priority to lowest priority. So let's say you enabled timer 0 and timer 1 interrupts, and they both overflow at the same time. The timer 0 interrupt will always be serviced ahead of the timer 1 interrupt, normally. If, by the way, while you're servicing one of these interrupts, one of these other interrupts happen, that will be acknowledged, it will be stored somewhere, but that interrupt won't be dealt with until the end of the interrupt routine that you're currently dealing with. Now, it's also associated with interrupts, so this is the strict sequence. There is another register, which I haven't shown you yet, called the interrupt priority register. So far, we've dealt with the register called IE, the interrupt enable register. There is another register called the interrupt priority register, where even if you're in one interrupt, if a higher interrupt comes along, you can stop doing what you're doing in the current interrupt routine and deal with the high priority interrupt routine. Yeah?
This priority here, if you're in, say, timer 1 interrupt,
Yeah.
and then external interrupt 1 happens, it switches over, right?
It wouldn't, no. What if once you're actually in, once you're in the interrupt routine, you would carry on. It wouldn't suspend the existing one.
Even though this priority is...
But if they happen at the same time, it would determine the sequence.
Oh, right, okay.
So it's just for what would happen under those circumstances. The flag for the other one would be set, and at the end of it, you would go into that one. So this is the priority register. Now, under these circumstances, what you can do is for any of the other sources of interrupt, you can elect to make them higher priority. What that means is, now this is different, if you're in, for example, an existing interrupt service routine and a higher priority interrupt is triggered, you can suspend the interrupt routine that you're in and deal with the high priority interrupt. So, and you can basically, by putting a 1 in any of these locations, you're making it high priority. Now, for example, if we go back one slide, let's say I've got two sources of interrupt, timer 0 interrupts and external interrupts. Now, if they both happen at the same time, the external interrupt will always win and always get serviced first. But I might not want to do that. I might say, timer 0 is more important to me than the external interrupt. What I could do is to make this source of interrupt higher priority. So if they happen at the same